Hi, everyone. Welcome to the Wherobots live stream. My name is Will. In today's session, we're going to do a bit of a hands on tutorial working with real estate data. So, I'd like to dive into Wherobots Cloud using Sedona DB. We'll write some spatial SQL, create some visualizations to take a look at changes in real estate value in the US at the county level. So if you're watching this live, feel free to drop your questions in the chat. I'm monitoring the chat over here. I can see those. So um, definitely like to keep this as interactive as possible. And if you're not watching live, feel free to also let us know in the comments any questions you have. We'll be sure to follow up and also let us know what kind of content you'd like to see going forward. If there are specific types of geospatial analysis that you're interested in, tools, data sets, this kind of thing, definitely let us know. Great. Well, like I said, my name's Will. I work on the developer relations team at Wherobots. So largely my job is to help developers and data scientists work with geospatial data using tools like Sedona DB, Apache Sedona, and Wherobots Cloud. So let's go ahead and jump right in. I'll share my screen here. Great. So, if you're not familiar with Wherobots makes a geospatial analytics database called Sedona DB. Sedona DB has functionality for large scale geospatial analysis. So, things like joining data based on spatial relationships, fitting data into your data pipeline, and then being able to do large scale analysis, write out the results of some analysis to the rest of your pipeline, typically for uh, things like AI or machine learning pipelines. Wherobots was founded by the creators of Apache Sedona, which is sort of the core for large scale geospatial functionality built on top of Apache Spark and Apache Flink. We are going to be using Wherobots Cloud today, which is built on top of Sedona DB, which extends the functionality of Apache Sedona in a cloud native cloud service called Wherobots Cloud. So let me drop a link in the chat to Wherobots Cloud. Wherobots Cloud has a generous free tier, so that's what we're going to be using is the free tier of Wherobots Cloud. You can just go to that link to create an account and sign in. I've already done that. This is a fresh account on the free tier of Wherobots Cloud. So you'll notice here, this is the first screen that you'll see, which is prompting you to start a notebook environment. So the notebook environment, this is the primary interface for working with Sedona DB in Wherobots Cloud. So I'm going to go ahead and start a notebook environment. And this will take a few seconds to spin up. You'll notice here that there are some default configuration options. We'll be running Sedona DB. We can see the versions of the different dependencies that we're running on, including Python, Spark, and the 1.0 version of Sedona DB. We can also configure our driver instances resources and advanced configuration to also configure different executor types and add more to our Spark configuration or even install different Python libraries. We're just going to use the default configuration today. So I'm going to jump into the notebook environment here. And we'll see this is a Jupyter Lab environment. So if you've used Jupyter Lab, the core experience of Jupyter Lab is based on Jupyter notebooks. So I'm going to go ahead and create a new notebook. And we're going to be writing Python today. And so we'll be using the Python API for Sedona DB in Wherobots Cloud, and we'll also be writing some spatial SQL. So let's go through what we want to accomplish today. And I'll share a few links to get us started. So in November was the 30-day map challenge, which if you're not familiar with this, the 30-day map challenge is kind of a challenge for folks interested in cartography, analyzing geospatial data, creating maps. And the idea is each day there's a theme. The goal is to create a map and post that out onto social media. And so I thought it would be fun to play along a little bit here. I did a few of these. I certainly didn't do the full 30 days. I'll drop a link to this GitHub repository. So you can see I did a few of these. Each one of these has a link to the code in a Jupyter notebook, which you can upload into Wherobots Cloud and follow along. This is one that I did looking at calculating the range of different bird species based on observations from Bird Buddy. This is a fun one. Bird Buddy is a smart bird feeder that publishes data about bird observations and different locations. And so we went through that, and we saw how to calculate the range using convex hull operations and spatial SQL, and we used felt to create a map. So there's a handful of these. What we're going to work through today is one of the ones that I did for creating choropleth maps, looking at change in home value in the U.S. by county over the last 5 years using data from Zillow. So we're going to reproduce this notebook that I created. So if you're interested in the code, you can find that online here in this GitHub notebook. Cool. So we're going to be using two data sets to do this. So for our housing data, we're going to use data from Zillow. So Zillow publishes a couple of interesting data sets. I'll drop a link to that in the chat here. So Zillow publishes home values in the form of the Zillow Home Value Index, or the ZHVI. And they publish this going back a number of years. I think going back to 2010, I think is the first year that they have data for. The data back going back too far is a little bit sparse. So we'll just look at the last 5 years. And you have different options for geography. We're going to be doing this at the county level. So this is a data set we're going to be using, the ZHVI, Zillow Home Value Index. And specifically, we're going to look at the seasonally adjusted time series data set. There's also data on home value forecast, data going forward, the rental market, as well as sales, time on days on market, this sort of thing. So Zillow is going to be the main source of data for our change in home value time series data. And then we said we're going to do this at the county level. So we're going to use a data set from Natural Earth to keep track of the county geometries. Natural Earth, this is a free data set with raster and vector data. This is used a lot in cartography or really any sort of geospatial analysis project. We're going to use the large scale cultural data set and specifically the admin 2 level, which is counties in the US. But you can see here there's lots of great data sets, things like roads, populated places, national parks, counties, states, these kinds of things as well. So I'll drop that in the chat. Great. So I've already downloaded these data sets and uploaded them to Wherobots Cloud, but I want to show how we can do that. So we saw that Wherobots Cloud gives us this notebook environment, and we spun up and created our first notebook. We haven't written any code yet. And obviously, the first thing we're going to want to do is be able to access the data in our Whereabouts Cloud environment. So Whereabouts Cloud gives us free S3 access. So if I click on the Files tab here, and by default, any notebooks that I create are saved into this notebooks folder. But I also have this data directory. These are created for me specifically and can be shared throughout my organization as well. I can have different whereabouts user accounts connected to an organization. So I've uploaded the data here, just using this upload file button. And you can see I have two data sets. I have this CSV file that I downloaded from Zillow. Zoom in a little bit here. So this is the ZHVI time series data. This is a flat file, a CSV. And then I created a directory for the Natural Earth shapefile data set. So shapefiles, these are Esri's kind of older school format for working with spatial data. A shapefile, confusingly, is not just one file, right? It is multiple files. And so when I reference this data set, instead of referencing a specific file, I'm going to be sure to reference the data directory when I start importing that. And so these files are stored on Amazon S3. They're private to my account in Whereabouts Cloud, private to my organization, and I get this S3 path URL that I can copy to reference in the notebook environment. So I'm going to go ahead and copy this S3 path, and we'll go back to our notebook environment, and let's go ahead and get started. So we didn't take a look at some of the existing notebooks, but if we take a look at the existing sample notebooks, there are quite a few in here that show how to work with different features of Whereabouts Cloud. We're going to skip those and just create our own notebook from scratch here. But there's a kind of a few things that we'll pick up if we'd looked at some of the previous notebooks that give us an idea of kind of the common structure for getting started with Sedona DB in Whereabouts Cloud. The first thing we're going to do is import some dependencies. So we're going to import the Sedona.Spark package. We'll import a few things later on, but this should be enough to get us started. And then the other thing we're going to do is configure our Sedona context. And this is something we do. We can assign a name here. This is something we do to spin up a Spark cluster behind the scenes once we do this. And typically, in this config object, we might do things like pass credentials for accessing certain S3 buckets, certain data sources, things like that. We're just going to use our connection to data in Whereabouts Cloud, so we don't need to worry about that. That's going to be our configuration object, and then we'll go ahead and instantiate our cluster. That config object. And what what did we do wrong there? Config. Let's let's grab. I have another example over here. Let's go ahead and paste that in. We had a typo there somewhere. Okay, so this will take a moment to spin up our Spark cluster. So Sedona DB adds geospatial functionality on top of distributed compute frameworks like Apache Spark, which is why we're spinning up this Spark cluster. And the benefit of Wherobots Cloud is it's a managed cloud service that manages that cluster for us and manages the complexity of that, which is quite nice. Let me zoom in a bit more. About as big as we want it. Great. So the first thing we're going to do is import the Natural Earth shape files. And so let's go back to the files UI. We're going to copy the S3 path for the directory where we have saved those. And now I'm going to import a couple more packages to be able to import the shape files. So from Sedona core format mapper shapefile parser, we're going to import the shapefile reader. And from Sedona utils, we import adapter. We take a look in the documentation, and I'll drop a link to this in the chat as well. This is the documentation for Sedona DB and Wherobots Cloud. There's lots of useful information in here for how to work with our Wherobots Cloud account, how to work with the notebook environment, lots of features in Wherobots Cloud that we're not discussing today, like creating recurring jobs, these sorts of things. But we also have information about working with data. One of the benefits of Sedona DB is being able to load data from pretty much any spatial format, any data format that works with spatial data. So these are things like flat files, CSV, shape files, GeoJSON, GeoParquet, loading data from PostGIS database, these kinds of things. And we can see the example here of how we can load shapefile data. So we're going to follow these instructions here from the documentation to import our Natural Earth county shapefile data. So what we're going to do is first create a spatial RDD by using the shapefile reader. Say read to geometry RDD. So what is a spatial RDD? Well, RDDs or resilient distributed data sources are a core data structure in Apache Spark. They allow us to distribute large data sets throughout a Spark cluster. And some of the core functionality that Sedona DB and Apache Sedona introduce is what's called a geometry RDD. So basically extending the concept of a Spark RDD, adding geospatial functionality. So things like having a geometry associated with the RDD and adding functionality for geospatial querying, geospatial indexing, geospatial partitioning, these sorts of things. So the spatial RDD is one of the core structures that we see in Apache Sedona and Sedona DB. So we're going to use the shapefile reader and our Sedona context, and we'll point that at our S3 URL. Now, we don't, in this case, typically want to work directly with the spatial RDD directly. We want to convert that into a spatial data frame. So we'll say county DF is going to be, and here's where we're using the adapter. So we'll convert our spatial RDD into a spatial data frame. And then the next thing we'll do, since we want to be able to query this data frame using spatial SQL, which we'll talk about in a minute, we're going to create a view, call that counties, which will allow us to query that data frame using spatial SQL or the Python API. And then we're printing the schema of that data frame. And so this is the schema of the data frame, just reading directly from the shapefile. So we have a geometry column, and then we have lots of attributes. So in this case, each row is a county. Counties have things like a name, a FIPS code. Natural Earth provides names in lots of different languages, which is quite nice. But now, since we created a view for this data frame, we can write SQL. So Sedona DB supports spatial SQL, which is an extension of, in this case, Spark SQL. So we have all of Spark SQL functionality available to us with some additional spatial functionality. So let's just take a look at a few rows of our data set. And I like things to be lowercase, so we'll just alias a few of these. Just the first 10. So if I run this, this is going to give me a data frame. I have a typo in there. Name in E. Oh, yeah, name EN for English. So if I run this, this is going to give me a data frame. So I can add a dot show to that to render the first few rows of that data frame. So we can see we have a geometry column. We have FIPS. FIPS is a identifier that's used for uniquely identifying administrative units. In this case, each one of these codes is unique to a county, and then we have the name of the county and the state of the county. And we can see here that our geometry can be different types. This is being rendered as WKT or well-known text. In this case, some of our counties are going to be multi-polygon, so complex polygon objects where we may have things like holes or multiple disjointed polygons. But I imagine most of them are going to be polygon geometries. We can visualize these using let's use the Sedona Kepler. So Sedona Kepler, if we look at the documentation, is one of our visualization options that is built in to jump to this page. That is built into Sedona DB and Wherobots Cloud. This is a wrapper around Kepler GL, which does a pretty good job of providing large-scale data visualization for geographic data that is accelerated by the GPU. In this case, we'll just pass our data frame and title. And so this will render in our Jupyter Notebook environment a geospatial visualization. So this will give us a map visualization showing each row in that data frame. And one thing that's nice about Sedona Kepler is that it's an interactive visualization. So there are 3,000 some counties in the U.S. So here we can see all of those rendered and interactive in the sense that we can hover over these. We could even go in and filter these if we wanted to style them differently as well. So Kepler is a nice interactive visualization style for working in the notebook environment. Okay, so that was, I'm just going to change this to markdown format so we can have a little placeholder in our notebook here. Okay, so far we've loaded the uh, natural earth shapefile with our county geometries. The next thing we want to do is load our CSV file that we downloaded from Zillow. So if I go back to the file browser, and if I take a look in my customer directory under the data directory, I've uploaded the CSV file for our Zillow home value index. So this is a time series data set of home value by zip code in the US. Let's save this URL as ZHVI. Cool. So we saw how to import shapefile data. This is a CSV. So in this case, we can just read that directly. Sedona read format is CSV. In this case, we do have headers and the delimiter is a comma. So this is a true uh, comma separated value file. Sometimes we have, delimited by tabs, things like that, tabs or pipe delimited. And we're going to read this directly from S3. Okay, so this is going to give us a data frame. So I'm going to create a view so I can query this using SQL. And then let's go ahead and print out the schema. We can see what that looks like. And so we have just a few attributes for each observation. We have the region name, state, metro area, and then we have the FIPS code again here. And then we have, looks like an observation for each month going back to the year 2000, all the way up through the most recent month that's available, which is ending end of October 2023. Cool. So let's see how we can query this data set using SQL. Let's pull out just a few columns here. So region name, state name, state. See what the data looks like here. Now, in this case, we have two columns. So everything, right? Two columns for the FIPS code here. And let's just bring through one of these time series, so it's the value of the index. I need to put that column name in backticks in this case. uh, since it starts with a number. And just the first 10 here. And again, this is going to give me a data frame. I probably have a typo in there. Municipal FIPS is, municipal code FIPS. Again, this gives me a data frame, but I want to just add a dot show there to view just the first few results. Cool. So this gives me the name of the county and the index value. So you can see how that single value is changing over time. What I need to do now is join these two tables, these two data sets, because I want to visualize the the data. I need to join the geometry from our shapefile onto our uh, time series data. And then we'll also need to do things like compute the change in value. We're not interested in just the most expensive counties. We want to know also how that has changed over time. So we're going to do this using SQL. And we'll create a new data frame. And let's grab just the most recent month. And so we'll cast that to a numeric value by default when we read in through a through a CSV. Values are strings, so we want to be sure we're casting that to a numeric value. Um, because we're going to be joining across tables, we need to specify which table, which view that's coming from, and we'll grab the most recent, which is ending October. Cast that to a float. We'll call this value. This is going to be the home value in that county for that month. The region name is the name of the county. And then we want the geometry of that county from the counties table. So those from CHVI, join the counties table on the FIPS code, since that's the unique identifier that we have in common between both of these tables. So if we note, though, we said we had two FIPS codes. It's broken up into a state code and a municipal code in the Zillow data. In the shapefile data, though, we have just a single FIPS value. So we'll need to figure out how to deal with that. So what we want to do is say something like ZHVI dot state code FIPS equals counties dot FIPS. And then let's just show the first 5 rows of that. And this is going to give us an empty table because again, we need to massage these FIPS values a little bit. So we're going to use the concat single function to concatenate our two FIPS values. And again, if you notice, the Natural Earth FIPS value starts with US, and then the state code FIPS, and then what Zillow is calling the municipal code FIPS. So we'll concatenate those 3 values. HVI dot municipal code FIPS. And let's exclude Alaska and Hawaii. Just from looking at this data previously, I know that data it's a little sparse in Alaska and Hawaii. Great. So now we've joined these two data sets. So we have the index value for the most recent observation. We have the name and the geometry of the county. That's great. We can visualize this using another built-in visualization option, in this case, Sedona PyDeck. And what we want to do is create a choropleth map. And now a choropleth map is going to be a visualization where we're mapping surface area, colors, typically to some value, some range of value. So we're going to be using the ZHVI county data frame, and in this case, the value, the column that we want to visualize is just called value, which is our index. This is going to give us a choropleth map using DeckGL, which is, again, I think that's kind of a foundation to Kepler GL, which we saw earlier. So Kepler GL, we're visualizing all of the counties. Now, with our choropleth map, we want each county to be styled a little bit differently, indicating some difference in the value. And by default, the color scheme uses a range of opacity. So you can see here, there's this Teton County in Wyoming. This is quite a bit of an outlier. Pitkin County in Colorado is also quite a bit of an outlier. You can see on the East Coast also some outliers. So again, the built-in visualizations, things like Sedona PyDeck and Kepler GL are great for creating these interactive visualizations. Let's see how we can create maybe a more static visualization using matplotlib. So one thing that's nice about Wherobots Cloud and Sedona DB is this pretty seamless integration with the PyData ecosystem. And so what we're going to do here is create a GeoPandas geodata frame. Now, a lot of things are installed by default in Wherobots Cloud in the Jupyter Notebook environment, which is quite nice. So I don't need to install GeoPandas. I can just import it. If you used GeoPandas before, or if you haven't used GeoPandas before, GeoPandas is a extension on Python pandas data frame, similar to the way that a spatial data frame in Sedona DB is an extension to a Spark data frame. Geodata frames add a concept of geometry and geospatial querying functionality to Python pandas data frames. In this case, the reason we're going to convert our our spatial Spark data frame to a geodata frame is so we can pass that to matplotlib to do some basic visualization to create a static choropleth map using some of the Python tools. I'm also going to install a package. So we said that lots of Python spatial packages are available already installed by default. We can also specify those in the UI when we instantiate our notebook environments, but we can also install those either in the terminal in Jupyter Lab, or we can also do that in the notebook environment. I'm going to install the map classify package. And this is a useful package. Actually, I'm going to go ahead and link a chapter from a book that I found useful while putting this together. This choropleth mapping chapter from a spatial data science book. This is a good read if you want to go deep into learning more about creating choropleth maps and different ways of binning. So that's one thing we want to deal with here, is because we're going to have different outliers. If we go back to our data set, we can see here that we have a few outliers. We want to be able to specify binning for how we want to specify the distribution of that data set in our chloropleth map and how we want that to map uh, to our visual rendering of that. So let's go ahead and create our geodata frame from our county. So there's a two pandas method that we can call, and we need to specify the um, geometry column. And now to create a simple plot, let's render this using matplotlib. And we can see here, this is unprojected data. So we can see, this isn't typically the view that we're used to when we're working with um, choropleth. Choropleth visualizations, typically we want to use a map projection, and typically we want to use an equal area map projection. So something like the Albers equal area projection that is going to have less distortion of specifically the area, in this case at the county level. There are lots of different map projections. There's some really interesting science behind that. If you get into geodesy and how we can map the surface of the Earth to a two-dimensional map, but choice of map projection really depends on, I think, what you're trying to optimize for. So let's set the coordinate reference system to a projected coordinate reference system using the Albers equal area. And to do that, let's see, we need to first set the CRS, and initially this is going to be 4326, which is WGS 84, unprojected, and now we can say 2 CRS, I think is, 2 CRS. And the code for the Albers equal area is 326. No, not 4326. It is, check my notes here, 3857. That will reproject our data to Albers equal area. So now when we plot this, we have our projected data. Okay, so let's specify, I guess, first of all, the column that we want to visualize in our choropleth map. So that's value. And so this looks pretty similar to the choropleth map that we saw using Sedona PyDeck, where we saw our clear outliers here. So let's use a different scheme for how we're going to bin those values. And again, the choropleth mapping chapter from this geospatial data science book that I linked earlier goes into a lot of detail here, and some of the different options that you have for binning. And in this case, we'll use Jinx, which I think is a pretty common option. Okay, cool. So now that handles the distribution of the data a bit better. We can see some more nuanced pieces in our visualization, taking into account outliers and how the data is distributed. we can add a legend here. So we can see some specific values. This doesn't mean a whole lot in this context because we're looking at um, an index value. So that's and it's also seasonally adjusted. So it's not necessarily the case that this means that the average or median home price in a county is this value necessarily. And then we can also do some things here to make this a little prettier. Something like this handle on the plot. We can do things like axis off, since that's not super meaningful in this context. Um, we also might want to do something like turn off the legend, uh, these sorts of things. Okay, so this gives us, kind of an indication of, where the expensive counties are. We wanted to look at the change in real estate value over time. And to do that, we're going to go back to writing SQL here. So let's create a new data frame. We'll call this one the Delta County data frame. And again, we're going to write some SQL here. So in this case, what we want to do is compute the difference from, I guess specifically the percent change, I guess, from 2023 going back to 2018. And so to do that, again, this is going to be pretty similar to what we started off with. We're going to cast the most recent observation to a numeric value. So to calculate a percent change, we take the most recent minus the beginning period, and we'll use the 2018 value as the beginning period that we're going to look at. To a numeric value. And then we divide that by the beginning value, right? So cast VHVI 2018 31 as numeric value. And so let's just be very explicit and add a few parentheses here so we can see exactly what's going on. And then I'll also multiply 100. So we have percent. There, let's alias that, call that delta. Cool. And then, so that's going to be our change in value. We can also grab the region name, the state name, the geometry, and then let's calculate the centroid. Maybe we want to annotate the map with the most extreme values, the highest and lowest, and so we want to know the centroid, so a single point of each county. Okay, and then we need to join these exactly the same way that we did previously using the FIPS code. And again, we're going to need to concatenate a few strings here. So the state code FIPS plus the municipal code FIPS. So where that is equal to tips, and we're excluding Hawaii and Alaska. The county DF is what we're calling this new data frame, and we'll show the first 5. And I'm sure we have a typo. I'm missing my second backtick. And misspelled float. Cool. There we go. So now what we want to do is visualize the results as well. Again, we'll follow that same process, converting to a geodata frame. Is the toPandas method on our Spark data frame. Specify the geometry column. Cool. And then previously we did, we set the CRS to specify that, and that returns a new data frame. So we explicitly set that, and then convert CRS to all equal area, so that when we create our plot, we have the right projection for a choropleth. So we don't have any distortion in the area of each county. Cool. So in this case, let's specify the column that we want to visualize is the delta. And in this one, I went back and forth quite a bit on how to do the binning here. Actually, let's change our color scheme first. So we have um, data that is both positive and negative here, right? So we have some counties where the value declined over the last 5 years that we're looking at, and some where the value increased. So let's choose a appropriate color scheme for that, comma there. In this case, we want a color scheme that takes into account the data that's diverging about in this case the positive and negative. That's a pretty important indicator whether the data shows that the real estate value for the county increased or decreased. So we'll use this red, yellow, green color ramp to do that. And in this case, we're going to use not scheme, the user defined method to bin these. And so I'm going to specify classification keywords, and I'm going to specify my bins explicitly here. And the reason I'm doing this, and again, this is something that depends on the type of data that you're looking at, the distribution of the data, and the color ramp that you're choosing. But I wanted something that pretty clearly indicated to us when the data is positive or negative, to show us where we had counties with significant growth or decrease in price. What did we do there? So 0, 20, 40, 60, 80. Oh, right. You know what I did here is I realize that I forgot my order of operations here. And so we ended up with values not not represented as a sort of whole number percent. So going back to fix that. So now when we say that Whatcom County, the delta is 52, that means 52% rather than uh, point. Parentheses are important there. Okay, cool. So this looks a lot better. So now we can see where we have counties where the property values decreasing significantly, where they're increasing significantly as well. And we can, kind of style these. In this case, we can turn off the axis. We can set a title, home value change 2018 to 2023. Right, we need to get a handle on the plot. Go. Cool, and maybe the legend is helpful here, so we can see how those values changed and take a look at the outliers. Okay, great. Well, that is pretty much what we wanted to accomplish today. Um, Again, you can find the code for this notebook in GitHub. I'll drop the link to that in the chat. And we can also uh, find your access to Wherobots Cloud. Um, I'll drop the link to that in the chat as well. So just to recap a little bit, what we did here, we took a look at using data from Zillow and specifically the Zillow Home Value Index to see how real estate values changed over time in the US. We joined that with county level data from Natural Earth using Wherobots Cloud and Sedona DB. So we saw the file upload functionality in Wherobots Cloud. We saw how to import shapefiles and CSVs. We saw how to write spatial SQL. We saw how to visualize data using some of the built-in functionality in Sedona DB, including the Kepler and the PyDeck integration. Great. So I hope you enjoyed that. Feel free to follow along. And again, let us know in the chat what are some examples, what are some data sets you'd like to see as we are working with geospatial data using Sedona DB, Apache Sedona, and Wherobots Cloud. Thanks a lot. I hope you enjoyed that. Definitely, feel free to ask any questions in the chat, and we'll be sure to take a look at those and get back to you. All right. Well, again, my name is Will from the Wherobots Developer Relations team, and we will